morning, guys. Good afternoon. I don't know when you're interacting with this, but good, whatever time of the day it is. So, yesterday you talked about displacement, you talked about position, you talked about scalar and vector quantities, and I hope that that was okay. If you have any questions about that, please send me a question on the comments or as an email. Today I want us to talk about time, speed, velocity, and some acceleration. Now, all physical quantities change if there has been a change in time, or you cannot observe a change in a physical quantity unless there has been a change in time. That's just obvious. If my position changes, it's because there has been a change in time. I cannot move from one place to another without there having been a change in time. I hope that makes sense. So, change in time would be something like the final time minus the initial time. If I moved from here to say Mukono and I started at 10 a.m. and I got there at 6 p.m., then my change in time would be the 6 p.m. minus the 10 a.m., which is some number, which you guys know. So yeah, change in time. Now, usually in physics, we always assume or always take the initial time to be 0. And if the initial time is 0, then the change in time is simply going to be the final time that you traveled for. So change in t is usually represented with the t in physics. Now, because time changes, we know that physical quantities like speed can change, like velocity can change. Before we go to velocity, the units of time are seconds. That's the unit of time. Now, moving on to velocity. Velocity, I hope you guys remember from the general formula that distance is equal to speed times time. So because distance is speed times time, velocity, on the other hand, being a vector quantity, would be change in displacement, the rate of change of displacement. Let me try to write that. Velocity would be rate of change of displacement. Now, this word rate is used a lot in physics, and every time you see the word rate, you should understand that there is an aspect of time changing. Something is changing with respect to time. In this case, your position is changing with respect to time. If it was speed, it would still be the rate of change of distance, right? Because your distance is changing with respect to time. If it was acceleration, this is kind of extrapolating it forward, it would be the rate of change of velocity, because acceleration is also a vector quantity. Now, velocity, going back to velocity being rate of change of displacement, I'm going to have change in displacement divided by time. Remember, rate means time is changing, and if time is changing, displacement is changing, so therefore velocity is the rate of change of displacement. I'm using this little symbol on top of the v because velocity is a vector quantity. The same symbol should appear on top of the x because all vector quantities in physics are denoted by that little symbol on top of the letter. On top of the letter. So velocity is rate of change of displacement. If I wanted to write this out in more specific terms, it would be final position or final displacement minus initial displacement divided by, again, it would have been change in time, but remember we said that if the initial time is always 0, then the change in time would simply be the final time, which in this case will just be t. So that's velocity. Velocity is rate of change of displacement. Speed, on the other hand, is just a v, and it will just be distance divided by time. Because distance is a scalar quantity, time, scalar quantity, and speed, in this case, would also be a scalar quantity. Now, the two aspects, average speed and average velocity. Consider somebody that moves from here. This is their home. It moves 4 meters. It can even be kilometers, and then 7 kilometers, and then another 4 kilometers, and then 7 kilometers back home. I guess it's kilometers. This person's average speed would simply be the total distance divided by the total time. So total distance is 14 plus 8, 22. Total time, let's say this thing took him 2 hours. His average speed would be 11 meters per second. That is his average speed. Now, his average velocity, remember, average velocity, what would that be? Would be his total displacement, not distance. Would be his total change in displacement. His total change in displacement divided by the time. So this just means sum. This symbol means sum in mathematics. I hope you remember. And when you look at this guy, his total change in displacement, he started here and he ends up here. His change in displacement is 0. And the time, it doesn't matter whether it's 2 hours or 50, but his average speed is going to be 0 meters per second. So that's kind of an interesting between average speed and average velocity. When you're driving a car and you look at the speedometer, do you think it shows you average speed or does it show you average velocity? And does it even show you the average speed? So that introduces us to something that's called instantaneous speed. When I have a position versus time, this is position, this is time. The position versus time graph of an object that's in motion. If the graph looks like this, I know you remember that that means that that object is moving at a constant velocity. If the graph, let's just review this really quickly. If the graph is like that and its position versus time, this object is at rest. If the graph is like that, position, time, this one is returning to origin or moving in the negative x direction. If it is position versus time, I think those are the ones. And it looks like this. That means it's accelerating or the speed is increasing. This is kind of looking forward. It's position time and it looks like that. Slowing down, going in the negative direction. So I hope we talked about this in your previous either physics or math classes. I hope you remember what they mean, right? So going back to this one here, this position versus time shows me that this object is going at a constant velocity. And if I wanted to find its average velocity, I'd figure out the total distance traveled or the total displacement divided by the total time. However, you guys know that if you're moving from your home to go to Acacia Mall, you're not going to have a constant speed or a constant velocity the whole time. Your actual graph would look something like this, that this is when you're stuck in traffic and then the lights let you go, and then, it's going to be something like that. I don't know what this is. Get rid of that. It's going to be something like that. So if this is your actual thing, what we have here is more of, an average of what your graph looks like. So that means your speed is different at different points throughout your journey, and that's what we term as instantaneous speed. Instantaneous speed is the speed at a given point in time of that journey. So your car speedometer shows you instantaneous speed. It doesn't show you your, average speed. It shows you instantaneous speed. And remember, it shows you speed. It doesn't show you velocity, because your speedometer does not tell you what direction the car is going. It only tells you how fast the car is going. All right, so that's average speed and average velocity. Now let's look a little bit at acceleration. think you remember from earlier, we said acceleration is the rate of change of velocity. Rate of change of velocity. So this can be written as final velocity minus initial velocity divided by time, initial velocity. So that's what acceleration is. I want us to look at position time graphs for different types of acceleration. And before we get there, on your worksheet I gave you different aspects of a motion of a car that could be accelerating. Because acceleration simply means that your velocity is changing. That's simply what it means. Velocity changing can be changing going up, speeding up, or going down, slowing down. It could be changing in the positive direction or in the negative direction. So I want us to specify what that exactly looks like. Now let's assume a car, these are arrows showing you the velocity of a car. These arrows are getting bigger and bigger, right? Since the arrows are getting bigger and they're going in the positive x direction, we're going to say positive, that direction is positive, so this means the velocity of this car is positive. It has a positive velocity. And since the velocity is positive, it's increasing, that means the car is accelerating and its acceleration is also positive, right? Okay, so another one is they're still going that way, but this time they are getting smaller, smaller and smaller. Now, since the arrows are going in the positive direction, this object still has a positive velocity. But these arrows are getting smaller. That means the car is slowing down. So it has an acceleration, true, but is the acceleration in this direction, or is it in that direction, right? So that's why it's interesting. For this one, the acceleration would be negative because it is slowing down. Its acceleration is in the opposite direction of its velocity. You could also use the word deceleration because it's in the opposite direction of where it is going. Another one is you have arrows going this way, getting bigger going that way, right? Velocity is negative, velocity is negative, and the acceleration in this case would be also negative because it is speeding up but in the negative direction. I hope that makes sense. It is speeding up in the negative direction, so it has a negative acceleration. Another case could be this. Now the intention is to draw all these arrows being equal. So it has a positive velocity, yes. What about acceleration? Since the arrows are not changing, that means the velocity is not changing, that means its acceleration is 0. Now what happens if they're facing the opposite direction? Same arrows, they're equal size, but they're just facing the opposite direction. This time velocity is negative, but acceleration, what do you think? Is it positive? Is it negative? Is it 0? Yes, it is still 0 because we do not have a change in velocity. Another one can be if these arrows are pointing that way, like that. Velocity is obviously negative because the arrows are pointing to the left. The velocity is negative. We know it has an acceleration because the arrows are changing. The size of the arrows are changing. What we want to figure out, is this acceleration positive or is it negative? Now, I hope you remember that in the first case, these arrows were increasing in these arrows here, the ones I'm talking about, they were increasing in the positive direction. It therefore had a positive acceleration. These ones were decreasing, but in the positive direction, but they're decreasing. So that means it had a negative acceleration. Trying to transfer that idea to what we have here, these arrows are decreasing in the negative direction. So what does that mean? We'll have a positive acceleration. It's as if it's like saying it's decelerating in the negative direction. So its acceleration is going to be positive. Now lastly, I want us to look at position time graphs. Position time graphs for each of these scenarios that we have looked at. I'll just try to draw them beside what we've already written. I'll try to make this smaller so that we can draw position time graphs. Guy was left out. Sorry, just gonna delete him. Hope you guys don't mind. Delete this one. Yes. Alright, so for this one, its position time graph, what is it going to look like? Positive velocity, okay? Remember, if the object is accelerating, this is the position time graph. If the object is accelerating, I expect that kind of shape for the graph, right? It's accelerating in the positive direction. This is what it looks like. What about this one here? Object is accelerating, but it is in the negative direction. It has a positive velocity. Sorry, it is decelerating in the positive direction. So it has a positive velocity, but the distance that it's covering in each time interval, is it going up or is it going down? That's the question you ask yourself. In this case, the distance covered in each respective time interval is going down, right? The distance in each time interval is going down and down and down. So that graph is going to look something like this. Because this means that in this time interval, I covered a big distance. But in the next equal time interval, the distance I covered went down. So this is the distance you're looking at in comparison with this one right here. And in the preceding time interval, equal time interval but distance covered goes down even more dramatically. So that would be the position time graph for an object that has positive velocity but negative acceleration in the positive direction. Alright, moving on to these ones. Just drawing their position time graphs and then we'll be done for today. You guys will just have homework to do. Alright, this one, position time graph. What do you look like, Mr. Position time graph? Alright, so it has a negative velocity and it has a negative acceleration. Negative velocity, just generally, negative velocity, that graph has to have a slope that's like that because that's a negative slope. So, because I know that that has to be the case, the distance, ask yourself, the distance being covered in each time interval, is it going up or is it going down? If this is the start, this is the 0 point, the distance covered in each time interval is going up, right? But in the negative direction. So if that object starts here, is its graph going to be like this? Would that be increasing distance in increasing time intervals, or is it going to be like this? Let's see. So in this first time interval, this is the distance covered, right? We want that distance to go up. In this time interval, this is the distance covered. That's not going up. So we know that that's not going to be its graph. Its graph instead, this one will help him, will be this. Because as the time intervals go up, the distance covered in each time interval is also going up. I hope you can see that from this graph. Alright, position time graph for this one, because it has a constant velocity, that's just going to be like this. same as this one here, because it has constant velocity, but that velocity is negative, it's going to be like that. And then finally, this one here, I hope you can already figure out what this looks like. It's going to look like this. So those are position time graphs for each of these different types of accelerations. Please go ahead and do the homework and complete the lesson worksheet. Bye.